Hello, welcome to my talk on physical modeling, Froude, Similitude for the physical modeling of marine structures. This is the second part of 3 talks on this topic, and in this talk, I will introduce the theoretical foundations on why and how we can carry out the physical modeling of marine structures. Let's watch the video of a scaled floating wind turbine test in the rear wave tank. This video was taken at the Rear National Ocean Test Facility in Cork. This ocean tank has a width of 16 meters, a length 35 meters, and a maximum water depth 3 meters, which can be changed by moving the movable floor for different water depths in the tank testing. The 16 segment wave makers are mounted at the near side, which could generate waves of maximum wave height 1.1 meter. This test model of a floating wind turbine has a control system on the tower. In the video, we can hear the low-frequency sounds from the wave makers and the high-frequency sounds from the tower control system. Unlike the numerical modeling, physical models could provide the most reliable data for the problems of the fluid-structure interaction. If the physical modeling has been carried out by satisfying the relevant similitude laws, the fact is that people believe in the tank test data much more than the numerical simulations. Even for the most advanced numerical simulations, the direct numerical simulation, DNS, would be validated using the test data. Therefore, the questions include why we can conduct the scale model test, or equivalent question would be, what is the theoretical foundation for the scale model test? The second question is how we can carry out the scale model test, or we can ask, what are the criteria for the scale model test? And in this talk, I will answer all these questions using the theoretical analysis. But here, we must mention that dimensional analysis is not a guide for the model test, but a method for simplifying the physical modeling. For instance, we might need to vary fewer parameters to get the relation among the variables. This is even same for the numerical modeling, in which we often present the result using the non-dimensional parameters. For instance, for many fluid structure interactions using the dimensional analysis, the target forces would be the function of the Reynolds and the Froude numbers. Hence, we do not need to study the relations among all the parameters as we have shown in the first part of the talk. However, the dimensional analysis does not tell us how we can meet all these criteria. For most problems of fluid structure interaction, the key issue is how to obtain the forces for studying the motion and the structural analysis of the marine structures. Basically, the force can be calculated from the fluid pressure, especially the dynamic pressure, and the skin drag can be calculated from the stresses on the structure surfaces. Mathematically, the force and the moment can be calculated as the integrals of the pressure on the structure surface, given as this. Therefore, the most important issue is to find the fluid pressure P. This is the most important issue for the numerical simulation and sometimes in the physical modeling test if we have enough pressure sensors. For this reason, we will start to examine the problem from the Navier-Stokes equation. For marine structure, the fluid can be simply regarded as the incompressible flows. Hence, the Navier-Stokes equation would have a simple form as this continuity equation and the moment equation given in this form. Now, we look at two geometrically similar systems, S1 and S2, with the characteristic lengths L1 and L2. In the published paper I did in 2014, I first ever did such an analysis using the Navier-Stokes equation to look at the key issues for the physical modeling. Here, we can take these two systems, S1 and S2, are different because the control equations, the Navier-Stokes equation for both systems are same, but the boundary condition would be different because we have different sizes of these two systems. The first thing is that we normalize the Navier-Stokes equation using the non-dimensional parameter x prime, y prime, and z prime, for which the coordinates x, y, and z are all normalized by the characteristic length L. As such, geometrically, we can transform the original system S to a transformed standard system S prime, and the transformed standard system has a unit characteristic length 1 here. In a similar way, we can normalize the velocity using the characteristic velocity u as this, and the non-dimensional pressure as this p prime, and the non-dimensional time t prime. Applying the non-dimensional parameters to the Navier-Stokes equation, we have the transformed non-dimensional continuity equation given in this form. And for the momentum equation, the transformed non-dimensional moment equation are slightly different. We compare these two Navier-Stokes equation, we can see in the non-dimensional momentum equations, we have the non-dimensional number Re, the Reynolds number, defined in this formula based on the characteristic length L and the velocity U. Another difference is the Froude number Fr, which is defined in this form. As such, we transform the dynamic system S to the normalized standard system S prime, and their governing equation are the normal Navier-Stokes equation and the transformed Navier-Stokes equation, respectively. Now we return back to the geometric similar system S1 and S2. For the system 1, we can make the normalization for the system. Geometrically, if we made the non-dimensional analysis, we can transform the system S1 to the standard system S1 prime as this, and the dynamic equation, the transformed Navier-Stokes equation for the transformed system S1 prime, given in this. Again, we can see here the Reynolds number and the Froude number in the transformed Navier-Stokes equation for the system 1. And for the system 2, similarly, we can use this non-dimensional analysis. We can transform the system S2 to the standard system S2 prime, and the corresponding governing equation are this transformed Navier-Stokes equation with the Reynolds number Re2 defined as this and the Froude number Fr2 given by this. Now we can compare these two transformed standard system S1 prime and S2 prime. Geometrically, these two transformed systems are same, we can see here, but dynamically they are different because their governing equations, the corresponding non-dimensional Navier-Stokes equations are different. If the Reynolds numbers Re1 and Re2 are not the same, and or the Froude number Fr1 and Fr2 are different, this means these two transformed standard systems S1 prime and S2 prime are dynamically different. For the transformed standard system S1 prime and S2 prime, they are geometrically same, but they are kinematically and dynamically identical only when the Reynolds numbers Re1 equaling to Re2 and the Froude numbers Fr1 equaling to Fr2, or in details given in these formulas. Under this condition, then the transformed systems are geometrically and dynamically identical. Thus, we can say these two systems are same. S1 prime equals S2 prime. We have shown when the Reynolds numbers Re1 equals to Re2 and the Froude number Fr1 equals to Fr2, then we have the identical transformed system for the system S1 and S2. Here, we use the single transformed system S-prime as the transformed system for these two systems S1 and S2. Since the transformed system for these two systems S1 and S2 are identical, so we can see the non-dimensional parameters x1 prime equals to x2 prime as this. Now from the definition of the non-dimensional parameters, we could have this formula, and then we can define a scaling factor epsilon as this. This scaling factor is for the scaled model S2 with regard to the original system S1. In this talk, we start from the incompressible Navier-Stokes equation and deduce that the Reynolds and the Froude numbers are the most important factor for the similitude laws. This is consistent with the dimensional analysis, but here we can see more details from the analysis directly from the Navier-Stokes equation. That is, if we want these two systems, S1 and S2, to be dynamically similar, we must ensure both Reynolds numbers and Froude numbers for the two systems S1 and S2 must equal respectively. According to the reference, we have many more non-dimensional numbers. In the paper, 21 different non-dimensional numbers have been listed. But in fact, there are more non-dimensional numbers or parameters used for different applications. Here, I choose some of the non-dimensional parameters. The Reynolds number would ensure the similarity of viscous force between the system S1 and the S2, while the Froude number ensures the similarity for the gravitational force, which is the main force for the ocean waves. However, for different applications, different non-dimensional number would be used. For instance, in the aerodynamic application, an important non-dimensional number is the Mach number, which is especially important for the compressible flows, when the flow velocity or the relative velocity is close to or larger than the speed of the sound. In some other applications, Nusselt number, Strohard number, and the cavitation number might be used for different purposes. In the last part of the talk in this topic, I will talk about how we can meet the similitude laws for the scaled model test.